In this video, what I'm going to be discussing molecular orbital theory or molecular orbital diagrams. And I've got 4 of them drawn here. I'm going to do the molecular orbital diagram for you folks for the first 10 elements on the periodic table. Now, molecular orbital diagram theory is kind of neat in that it combines atomic orbital theory, which has some deficiencies, and molecular orbital theory predicts things such as magnetic properties of materials. It also predicts spectroscopy. It also can predict excited states. It can also predict how molecules can absorb light. So molecular orbital diagram theory, molecular orbital theory is much more powerful than atomic orbital theory, but it's a little bit more complicated. The idea behind molecular orbital theory is that atomic orbitals mix to make molecular orbitals. So for instance, for the first example we'll look at hydrogen. And so we're going to use H2 as going to be the first example. Now, if you look at the electron configuration for hydrogen, it's going to be 1s1. So each hydrogen molecule is going to put in an electron into the 1s orbital. So it'll be the 1s orbital. Now those 1s orbitals are going to mix and they're going to produce sigma orbitals. And this happens to be a sigma 1s. This is going to be bonding. And this up here is going to be the sigma star 1s. And this is anti-bonding or non-bonding. And what happens is when you put electrons into the bonding orbital, you produce a chemical bond. When you start putting electrons into the anti-bonding orbital, you break chemical bonds, and that it's more energetic for it to be, it would much rather be apart than it would be together, is what happens when you put electrons in there. From molecular orbital diagram, or molecular orbital theory and molecular orbital diagrams, you can come up with what's called the bond order, or the number of chemical bonds that will be in a material. Now for this one, we'll put these 2 electrons into the bonding orbital. Another thing to note is that if you have 2 atomic orbitals, you're going to make 2 molecular orbitals. Now since we've put these 2 into the bonding orbital, we can now calculate the bond order, and the bond order is going to be equal to 1/2 times the bonding electrons, there are 2 in the bonding electron, minus the anti-bonding or the non-bonding electrons. And in this case, this happens to be equal to 1. This happens to be equal to 1. Now, there's a shortcut notation for writing molecular orbital diagrams. And that shortcut for this is going to be, this would be sigma 1s2. Would be how you, instead of constantly having to write these molecular orbital diagrams, you can come up with a shorthand notation such as this. Now, we only have 2 electrons here, so we can only put 2 electrons into the molecular orbital diagram. If we move over here and do helium 2, we can do helium 2, and this would be the 1s, this would be the 1s, this would be the 1s for one of the heliums, and we know that there are 2 1s electrons for each helium atom. If you look at the electron configuration for helium, it's going to be 1s2. Likewise, this is going to be a sigma 1s. This is going to be a sigma 1s star. This is the bonding orbital. This is the anti-bonding orbital. We have 2 atomic orbitals. We're going to have 2 molecular orbitals. So as we start filling in to the molecular orbitals, we have 4 electrons. We have 2 here and 2 here, so we must have 2 here and 2 there. So now we've put electrons into the molecular orbital, or to the anti-bonding orbital. And so the bond order for this is going to be 1/2 times, now we have 2 in the bonding orbital, we have 2 in the non-bonding orbital, and so 1/2 of 0 is equal to 0. And what this tells us is this is going to tell us that H2 does not exist. There is no bond between H2, and we sort of knew that. Now, what would be the shorthand notation for this? Well, the shorthand notation for helium is going to be sigma 1s 2, and then it's going to be sigma 1s star for the antibonding orbital 2. All right. Now we can drop down to the on the periodic table and we can come up with lithium. We can look at lithium. So we'll look at lithium 2. Now, these, due to the space on this board, these two orbitals would actually be below here, right? This one would actually be below here because for lithium, it's going to have a 1s2, and then it has a 2s1. It has a 2s1. I'm only going to do the valence electrons because just simply for space on this board. But down below what you would have is you would have this exact orbital down here for the 1s electrons of the lithium. Now this is going to be sigma 2s, and this one will be sigma star 2s. We have, once again, 2s electrons. They're going to mix to make 2 molecular orbitals. So we have 2 atomic orbitals, and they're going to mix to make 2 molecular orbitals. We put these 2 electrons into there because that's all we have left. And so now we can see that the bond order for this is going to be 1/2 times 2 minus 0, which is equal to 1. So there's going to be a single bond. The shorthand notation for this is going to be, it's very simple. It's going to be sigma 2s2. Now over here would be the core electrons. This would be the core electrons here. We're not too worried about that. I'm more concerned about the valence electrons. So this would be the shorthand notation for that, for lithium 2. The next one's going to be beryllium 2. So this one here is going to be beryllium 2. This is going to be 2s, the 2s. Now remember, beryllium is going to be a 2s2. These two 2s atomic orbitals are going to mix to make that's not 1, that should be 2, sorry. They're going to mix to make atomic, or mix to make molecular orbitals, and this is a 2s star. They're going to mix as such, and so the bond order for this is going to be equal to 1/2 times 2 minus 2, which is going to be equal to 0. Now, if we want to write the shorthand notation for this, it's going to be those core level electrons, and then it's going to be sigma 2s2. Oops, I keep running into that. And this one's going to, let me just rewrite this over here. Sorry, let's rewrite this over here. We'll get this back to where it was. And if we rewrite, I'm just going to rewrite right here. I have a lot of room here. If we write it here, it's going to be the core level electrons. Then it's going to be a sigma 2s to sigma 2s star 2, because we put 2 electrons here, 2 electrons there. That's what the 2's represent. When I come back from this, we'll move on into boron. We'll look at the boron one. That one's going to be quite a bit different, okay? All right, I'm back now with more complicated molecular orbital diagrams. And this is because we're going to be dealing with the p's. So far, we only were dealing with the s atomic orbitals. Now we're going to be dealing with the p's. And remember, we're going to have we could put 6 electrons into the p orbital. And so there's going to be, this could be the px, py, pz, px, py, pz. There are 2 molecular orbitals. This is going to be one. Here's another molecular orbital. Now there are 6 atomic orbitals, 3 and 3 is 6. Therefore, they're going to mix to make 6 molecular orbitals. 3 and 3 is 6. So let's see how we label these. Let's start with the next element, which is going to be boron. So this is going to be boron 2. Now boron is going to have one 2p electron. So this is going to be 2p, 2p. Now down here, how you label this is going to be the pi 2p. So this would be the pi molecular orbital. This is going to be the sigma 2p molecular orbital. This is the pi 2p antibonding molecular orbital. And this is going to be the sigma 2p antibonding molecular orbital. Now, because there are 2 electrons here, we're going to put 2 into the molecular orbitals. Now, remember Hund's rule in that they're going to be parallel spin. Now, this is a kind of an interesting result. Because you have unpaired electrons with parallel spins, this means this is going to be paramagnetic. And that means it's going to be attracted to a magnet. Now, if we want to come up with the bond order for this, so the bond order is going to be equal to 1/2 the bonding electrons, so that's going to be 2, minus the antibonding electrons, which is 0. This is going to give us a bond order 1, which is going to tell us that there's going to be a single bond in B2. Now, if we want to write the shorthand notation, we're going to have the core level electrons. Then we have the sigma 2s 2. Now, I did not put these on the diagram simply for space, but they would be down below here. This would be the sigma 2s antibonding orbitals, and there'd be 2 in that. Now we're dealing with the pi's, so this would be the pi 2p2. It's how you write the shorthand notation for boron, boron 2. Now the next element we're going to deal with is going to be carbon 2. Carbon 2, oops, get the yellow marker. These are going to be the 2p, these are going to be the 2p. Each carbon is going to have a 2p2. It doesn't matter where you put the electrons on the p's. This likewise is going to be pi 2p. This is going to be sigma 2p. This one's going to be the pi 2p antibonding orbital. And this is going to be the sigma 2p antibonding orbital. And we're now going to put these 4 electrons into here. And so we can align them into the, so we'll take them out of the atomic orbitals and put them into the molecular orbitals as such. Now this we can see is going to be diamagnetic, meaning it's not going to be attracted to a magnet. It's not attracted to a magnet. Now if we want to come up with the bond order for this is going to be equal to 1/2 times the number in the bonding orbital, which is 4, minus the number in the antibonding orbital, which is 0. This will give us a bond order of 2. If we want to come up with a shorthand notation for this, it's going to be the core level electrons, sigma 2s 2, sigma 2s antibonding 2. Remember, the 2s are going to be down below here. I just didn't draw them for space. Then it's going to be the pi 2p, and we have 4 electrons in that. When I come back, what I'll do is I'll work on nitrogen and oxygen. And there it gets a little complicated, okay? Okay, I'm back with more molecular orbital diagrams. And we're going to move on. The next one's going to be nitrogen. The next compound we'll look at will be nitrogen. So N2. And once again, we have the exact same molecular orbital diagram. This is going to be the atomic orbitals. Those are going to be the molecular orbitals. And if you recall, nitrogen is going to be a 2p3. 2p3. Now, the reason I don't complete the arrow is that this represents an unpaired electron. And typically they leave an arrow out. I don't know why, but that's just how it is, how it's written symbolically. So we have 6 electrons here. We need to put 6 electrons into the molecular orbitals as such. So once again, this is going to be diamagnetic. I should go back to the pink one because that's what I was using. Anyway, they're going to be diamagnetic. If we come up with the bond order for this is going to be 1/2 bonding electrons, which is 6, 2, 4, 6, minus there are none in the antibonding orbital, and that's going to give us 3. So that tells us there's going to be a triple bond in N2. If we want to write the shorthand notation, That's going to be the core level electrons. And then we have the sigma 2s2. Remember, they're going to be down here. Then we have the sigma 2s star, 2 in there. Here, we then go up to the pi 2p, and we have 4 in there. And then we go to the sigma 2p, and we have 2 in there. So this should be the shorthand notation for writing a molecular orbital diagram where the electrons go. This would be analogous to the electron configuration, analogous to that. Now it gets complicated. Now is where it gets complicated. And this is, and what you'll see is for the most part, oh, I got ahead of myself. Next one is going to be oxygen, O2. And what you can see now is that the sigma star 2p and the pi star 2p are exactly the same. But what has happened is that the pi 2p and the sigma 2p switched positions. Now you would never know this, all right? This is not intuitive. How they found this out was through calculations and spectroscopic data. And so doing some experiments. And so they did some experiments. They noticed that spectroscopically, they noticed this is how the molecular orbital diagrams are. And this will be the one that will be for fluorine as well as the one for neon. We use the exact same one. So at nitrogen to oxygen, there's a switch in the bonding order. And this is now the sigma 2p, and this is the pi 2p, okay? Now, if you recall that oxygen is going to have a 2p4. 2p4. Remember, these are the atomic orbitals. These are the molecular orbitals. And now we need to put 8 electrons into here. So there's 2, 4, 6. And remember Hund's rule, this is now going to be 8. Because we have an unpaired electrons, because they're unpaired, this becomes paramagnetic. It's paramagnetic now because you have an unpaired pair of electrons. They're not paired up because of Hund's rule. If we want to come up with the bonding order is going to be, oops, got ahead of myself. It's going to be 1/2 the bonding electrons, so 2, 4, 6, minus the anti-bonding orbitals, so that's going to be 2. We do this arithmetic, this is going to be 4, half of 4 is 2, so this tells us that there's a double bond between oxygen. If we're going to come up with the shorthand notation for this, that was a terrible E. We're going to do the shorthand notation for this, it's going to be core level electrons, sigma 2s to sigma 2s antibonding 2. Then we're going to get the sigma 2p 2. This becomes pi 2p 4. And this becomes sigma 2p antibonding 2. And so that's going to be a shorthand notation for that. When I come back, we're going to finish this by looking at fluorine and then neon. Okay? I'm going to continue and conclude this talk on molecular orbital diagrams. The next one we're going to look at is going to be fluorine. Fluorine. All right? Now, fluorine is going to have an electron configuration of 2p5. So this would represent one fluorine atom, this would represent another fluorine atom. And it's going to have the exact same molecular orbital diagram that oxygen had and that neon will have as well too. So now we need to put 5 valence electrons in there, or 10 in total. There's 2, 4, 6, 8, and now 10. Now, if we want to come up with the bond order for fluorine, that's going to be equal to 1/2 times, this is 2, 4, 6. So we have 6 in the bonding, and we have 4 in the antibonding, and so that's going to give us 1. So that means that there's a single bond between the 2 fluorine atoms. If we want to write the shorthand notation for this, it's going to be the core electrons, then it's going to be the sigma 2s, 2, remember they're going to be down here, I don't have space for that. This is then going to be the sigma 2s antibonding 2. Now it's going to be the sigma 2p 2 because we have 2 in there. Now we get to the pi 2p, we have 4 in there. Now we get to the pi 2p antibonding, and we have 4 in there as well. Next, and finally, we're going to go to neon. This becomes now neon 2. Now neon is going to have, remember, a full octet, so it's going to have 2p6 in each neon. So this would be one neon atom, this would be another. So we have 12 electrons we have to put into this molecular orbital. So we filled up the entire molecular orbital now. If we look at the bond order, that's going to be equal to 1/2 the number in the bonding orbital. So that's 2, 4, 6. So that's 6. Minus number in the antibonding. This is the antibonding. There's 2, 4, 6. And so the bond order is going to be 0. So that tells us that neon will not bond. If we want to look at the shorthand notation for the molecular orbital diagram, it's going to be the core level electrons. It's going to be the sigma 2s 2, sigma 2s antibonding 2. Then it becomes the sigma 2p 2 gets us here. Then we get the pi 2p, and that's going to be 4. That's right there. Then it's the pi 2p antibonding up here. That's going to be 4. Then it's going to be the sigma 2p antibonding, and it's 2 in there. So this, as I mentioned, this shorthand notation is going to be analogous to the electron configuration, except it's going to be, instead of dealing with atomic orbitals as we did in the electron configuration, we're going to be dealing with the molecular orbitals. Now, something I wanted to mention was that these, I just want to remind you that the stars represent the antibonding. They're going to be higher in energy than the bonding. And so therefore, when you start putting electrons into here, you start making the molecule much more unstable. Makes it much more unstable. If you have any questions on molecular orbital diagram or anything else pertaining to this chapter, please let me know.